theory, but we don't have that yet. But we can see the strength of the forces looking like high energies that are converged. So the strength of the force changes as you change energy. So the electroheat force, that's where the heat boson lives in that part of the theory, and that's very well studied. So you could say, in this room temperature here, there are three distinct forces. So the strong nuclear force is sticking together quarks to make protons and neutrons. The protons and neutrons in the nucleus is a strong nuclear force. The weak nuclear force is radioactive heating decay, for example, and then electronegativity. So, and then gravity sits is the fourth force, which sits outside that theoretical framework at the moment, and that's relativity.
Is there a reason why time goes in any particular direction in quantum mechanics, or is it the same either way?
No, it's a parameter in quantum mechanics. I mean, so you go backwards from the quantum mechanics now.
Is there, because we see the world evolve in one particular direction at a time, is there, in quantum mechanics, is there a reason why? Is there a reason for that, or is it just the way it is?
I'm just trying to think if there's any. No, it's just I mean, quantum mechanics. It is a parameter, so there's really a time operator, but it gets a bit more. There are, I mean, there are formulations, I think, where people try to do something deeper. But certainly in the way that there's the standard version of quantum mechanics, no, it's a parameter. It's the same as in Newtonian language. It's just a thing. I mean, even think about it, even in Einstein's theory, there is there is such a thing as a clock that tilts. So massive particles have a lifetime, so and that's I think it's fair to say that's an input to the theory. So you're seeing we have what is there's such thing as proper time. There's a concept called proper time, and that's an axiom in relativity. As far as I can't think of any subtlety there, so I think you have to assume there's such a thing as time. I mean, it's true that the reason I'm just hesitating is so there are from the study of black holes now theories that are suggesting that space and time emerge from ultimately from quantum entanglements actually. So it's a theory that doesn't have space and time in it. But that's right on the edge of current understanding.
Because when you talk about quantum entanglement, is that not a violation of, because we only spoke about like future light cone, information can only be can only be transferred if light, the photon can travel that time as well, yeah. But is that violated with quantum?
No, it doesn't. So the quantum entanglement doesn't. It's been shown, and here's the experiment tested, that you can't transmit information through quantum entanglement. However, it is true that it feels like it violates the spirit of relativity, but it doesn't allow you to transmit, to communicate outside the light cone for events outside the light cone, for events outside the light cone, events to be communicated with. So it doesn't allow faster than light communication. And that's, yes, it's a standard proof actually. But if you're interested in that, look up Bell's inequalities, John Bell. So that was when that work was done. Good afternoon.
I have a question. So relativity is based on Einstein's postulates, and those are based off observations that made. Where because quantum mechanics is axiomic, where did other axioms come from? Because when you look at them, they're just like purely mathematical.
In quantum mechanics, where the axioms
Yeah.
or relativity as well.
No, the ones in quantum mechanics. Because
Quantum
they
mechanics.
don't seem to be based on like
There
actual
are
observations.
different ways in. I mean, again, it goes back to your question, which is quite a deep question, I think. It's what you can always ask, what are the fundamental things in physical theory? So what are the base assumptions? And you build the theory from those axioms, right? And you can choose different axioms, and you see it in quantum mechanics. There are different approaches. So, I mean, in relativity, for example, you can in our book, my book with Jack, we say we're going to assume that a theory of space and time has to be causal, so cause and effect. And you can take that approach, you go causality, and then you can sort of, from that, it turns out that you need some sort of speed that is a universal speed upon which everyone agrees in order to protect causality. Right? Or you can also say it is a fact that Maxwell's particle, that light goes at this speed, Maxwell's particle goes at this speed. Here is that, and that's the way Einstein did it, right? And then that's the way that he tells it in his course. Where you go, what are the consequences of the speed of light being constant for all observers? So you could say that. So I think the answer for me is that when you get these very rich theories, you can choose different axioms to start with, and you see it in quantum mechanics in different textbooks. You will start from different positions. Some of the advanced textbooks will start with purely mathematical ideas, like can we build a theory that has probability inherent in it, for example, and what would such a theory look like? And so then you can build from that. So one way of approaching it is to say, here is a mathematics, here is an algebra. So I've got this particular algebra. Does it describe the world? So you can imagine loads of different algebras, matrices, do things, and all that sort of stuff. And then you can build theories and say, do they describe our world? And that's one approach. So I think it's a good question. It's ultimately what we're trying to do is build models that give us predictions that we can test against experiments. And if you keep asking, well, why that model? Ultimately, the answer ends up being because it describes experiments data. Right? So I think that's probably the best answer I can give. It's the way that I look at it anyway, that we're building models of the world. And so, maybe it is, it's interesting, maybe it isn't the right question to ask, to put a lot of weight on a particular axiom. If you look at it in the sense that you're just trying to build consistent mathematical models that make predictions to the degree of observation, then maybe the axiom, that your way into that model maybe is not necessarily a profound thing. So yeah, you'll find many different ways into quantum mechanics. That's not my favourite book. Virtually every book you look at will start with different axioms in quantum mechanics. Basically, every textbook will start something different. Because that's your question about how did they find this stuff out in the first place, and it is astonishing when you look at history that people managed to build this theory when they didn't really know what they were doing. Right? It just turned out that when you calculate the things and it starts predicting the hydrogen atom spectrum from the Schrödinger equation and things like that, you start thinking, okay, there was something here. It's deeply baffling, actually.
Does the need to conserve internet information inhibit possibilities like genuine
That's a brilliant question, actually. The question is, does the need to conserve information inhibit the potential for genuine randomness? Because the way that it's a good question, because the way that we presented quantum mechanics here, which is basically the so-called Copenhagen interpretation, is that when you make a measurement, so you have this wave function that describes this ensemble of possibilities. And then when you make a measurement on the particle, then you'll find it is sunlight. So we looked at the expectation value, but of course if you say, where are you? Well, you'll say, I'm here. And the way that we talked about it in this course was to say, for example, you set up 1,000 systems with the same wave function, and then measure the position, measure the position, measure the position, and get the probability distribution. Right? So, but it's very true that you think of a single system, if that's the way that nature behaves, if you have a wave function, and then you go and make a measurement, and you say, right, it's there now, it's there. So your wave function has just gone to collapse, which collapsed to 100% possibility probability is there, which you just measure it. And then it'll evolve over time, and it'll spread out. So you then destroyed its past. So you did destroy the information. So that we don't think that it's pretty universally accepted now. That's not the right interpretation of quantum mechanics. Some people might disagree, but I think broadly speaking, that idea of wave functions collapsing is not the way that things happen. And so you get, for example, the so-called many worlds interpretation of quantum mechanics, which is wave functions don't collapse. So they don't. And then you've got to say, well, why does the we, what is happening to us then? What is happening when we make these measurements and these probabilities of real and so on? And the picture starts to be in the world interpretation. And all that happens is we're in the wave function. So for example, with if you're measuring, let's say you've got a wave function that says, you remember the one in the square well, where we had the wave function that had two parts, just the momentum either state. One was going that way, one was going that way. And we showed that those two projected that way, and we showed that it was an energy state, right? But you can express it as these two momentum either. So you could say, well, I'm going to measure it, I'll measure it. I'll make a measurement, I'll find out which one of these two possibilities is actually happening. And you find one, and you change the wave function. The many worlds interpretation is, no, what happened was there's now part of the wave function in which you measured the particle to be going that way, and another part of the wave function in which you measured the particle to be that way. So it's often said that the universe splits in two. It's not really, it's probably not the right language to use, but you just end up as part of the ensemble of probabilities. So there is now a world in which you measure the particles to do this, and there's a world where you measure it to do that, and off they go. And so that's the so-called many worlds interpretation, which is down to Hugh Everett, whose son is a founding here. But yeah, so it's a very wide part of physics, and getting more interested. It used to be, I should say, quite fashionable to work in the foundations of quantum mechanics. There was this kind of so-called shut up and calculate school, where we say, it doesn't matter, calculate the results of experiments, that's it, we're not to interpret what's going on in theory. But I think that certainly, when you think about cosmology, so quantum cosmology, it becomes a problem, because you can't, it's like saying, well, if the observer is a central part of our interpretation of theory, when you want to write down the wave function of the universe, then what do you mean by observer? There's no one outside you. So it's become much more interesting in the last few decades that people are really interested in what the theory is actually telling us about reality. There's a great book by Sean Carroll is worth reading, actually. He's a really great author, a very good physicist, and works a lot in these areas. So if you're really interested, there's a book called Something Being Forgiven that he wrote, which is a quote from Einstein. Which is a very good book on this. So I'd recommend Sean Howell books in this area. I think we should probably stop.
You're good? Got one more. You want to blame then, or are you happy? Got one.
What actually is
Hockey mediation. So it's, in principle, it can be all parts, but it's based on primarily, but in principle, it could be chemical fixes. In general, yes, photons, because they're masters. So that's not bad. Right, well, I can answer some more questions outside anyway, but thank you.